So we are, thanks for starting the recording. So Munich NLP is diverse community of people interested in NLP coming from industry, from academia, practitioners, and we host online talks like this one today, but also in-person events in Munich. And we have our own Discord server, which you are all invited to join. And we will just link it in the chat. So you also have it. I think it's the only way of getting here anyway. So you probably already are aware of the Discord server. But yeah, that's basically Munich NLP. And today our guest is Jason Lucas. Jason are you doing your PhD or in Penn State? Correct, yeah.
Yes, I'm doing my PhD fifth year. I'm now in my fifth year.
Ah, yeah, very, very good. Hopefully, it's coming to an end slowly.
Yeah,
But so his publications are in different topics related to AI safety. We were just talking about AI safety. I saw papers about detecting misinformation, also about low resource languages, and as today's topic is about machine-generated text detection. So there, Jason Lucas co-authored the benchmark Multitude, right?
yep.
And today we have another benchmark, which is the Beemo benchmark. And yeah, so if anybody during the talk has questions, they can write it on the chat. Other people can then thumbs up questions, upvote them or so, and we can prioritize them. I would suggest we can do like a little break in the middle for questions to any questions that have popped up, and also at the end you can also take some more questions if that's okay with you, Jason.
Yeah, yeah, that's fine with
Awesome.
me. Yeah.
Then I think that'll be it. I will pass on to you.
Thank you, guys. And if you have questions, feel free to write it in the chat and even put your hands up. If I see it, I would definitely stop, but I would do a hard stop in the center and take some question, and at the end also take some question. Thank you for the introduction. As he said, my name is Jason. Thank you to all the viewers online. I'm a PhD student at the Pike Research Lab at Penn State, and today I'll present Beemo, benchmarking of expert-edited machine-generated outputs, published at the NACL 2025. This collaboration is with Tokola AI, MIT Lincoln Lab, and the University of Oslo, addressing a critical gap in how we evaluate AI text detection when human edit machine-generated content, or vice versa. And this phenomena is consistent and integrating into our socio-technical system today. So imagine you're an educator, a researcher, a parent trying to determine if your student or child use generative AI like Claude or ChatGPT for assistance, then edit the AI output to make it read or seems more human-like. Or consider the reverse scenario. What if they wrote most of it themselves or ask a language model to publish a few sections? So the two question here is, do you have a keen enough eyes to identify which part are human versus machine generated? And if you resort to using some sort of tool, I know some people know Zero GPT, which you can use to detect machine generated text. How confident would you be in this software to determine whether your student or child would have used AI generated text? And I want you to hold on to these questions as I deliver this presentation. So why does this matter? Both expert and non-expert users today widely use LLMs for writing tasks, and I'm sure many of us, if not all of us on this call do. And this technology is rapidly adopting, creating a fundamental problem, particularly text authorship is no longer clear-cut in many domains like news, social media, science, and education. Meanwhile, we have research in machine-generated text detection that rapidly trying to address many of these challenges. However, Here's a critical issue. Existing benchmark focus most exclusively on binary single authorship scenario. So whether something is human written or machine generated. And this binary approach completely misses how people actually use large language model in practice. Most users don't just copy and paste AI output, they refine it, they may edit it, they may blend it with their own writing. So what does this mean for us? This means that current evaluation methods aren't equipped to handle this reality. To address this gap, we present three key contributions. First, Beemo itself, one of the first multi-author benchmark that includes LLM-generated responses edited by both experts and state-of-the-art models. This gives us a much more realistic picture of how text authorship work in practice, thus addressing this single authorship paradigm. Second, we conduct a comprehensive evaluation of 33 different machine-generated text detector configurations across 7 different scenarios. And this is a most thorough evaluation at that point of our research on how current detector perform when confronted with edited content, addressing another limitation for extensive evaluation on current tools. Third, we've made everything publicly available, so Beemo and all of its annotation materials are accessible via archive, GitHub, and Hugging Face, so the research community can continue to build on this work. In light of all of these contributions, it's worth stating that what makes Beemo unique is that it captures the real complexity of text authorship that is missing in existing benchmark. And these scenarios you may encounter in everyday life, like as parents, educators, and even researchers. So let me walk you through how we develop Beemo, as you can see in this diagram here. Our methodology involved 3 key stages as illustrated in the pipeline, A, B, and C. We have machine-generated text collection, we have LLM-based edits, and expert-based edits as well. So first, we collected machine-generated text from 10 different open source fine-tuned models. And here, I'll just give you a bit more details on some of these models. We use 10 diverse models that ranges from 2B to 70B parameters. Our model selection was intentionally diverse. We include different families such as Mistral, Llama 2, Gemma, and Mixtral, which is mixture of experts, to provide this comprehensive view of how various LLM generate text across different architecture and training approaches. Regarding the dataset, we utilize No Robots dataset as our source of prompts and human written responses, encompassing 5 practical use cases. This include open-ended generation, rewriting, summarization, and both open-ended and closed-ended question answering. Second, we had expert editing, and our expert editing process is the heart of what makes Beemo unique. We assemble a team of 25 expert annotators, all speaking their native English speakers from diverse education and demographic background. Importantly, there aren't just any annotator, they're experienced in refining LLM content, which was critical for the quality of our edits. Our editing pipeline was rigorous and it involved multiple quality control steps. So an editor would make the first rung of edits, then a lead editor would review and either approve the edits or send them back for revision. And this ensures consistency and high quality across our expert edited text. We set this apart from previous work in that we capture in real human expertise in editing AI content, not just mechanical transformation, but the nuance improvement that we might experience as editors ourselves or just expert editors actually making refinement of such text. And this is something that happened in reality humans tend to, refine text as they use AI to generate it to make it more realistic. So we try to capture this phenomena. So what exactly did we ask these editors to do? We provided them with a comprehensive guidelines that balances flexibility and consistency. The key instructions was to edit 20 to 40% of the text where possible. This gave us a recommended range while allowing editors to use their expertise and judgment. We asked them to address common LLM issues, such as correcting factual errors, fact checking where necessary, and refining text to make them sound more human-like while ensuring they're error-free. Importantly, editors could reject text if they are either too good to need editing or too poor to salvage effectively. So this mirror real-world scenarios where users might simply ask for a new response rather than trying to fix a problematic one. And I think the beauty of our approach is that we documented not just the guidelines, but also the actual editing strategy our annotators develop. And all of those can be found in our paper and our GitHub repo. So this isn't just a mechanical editing process. We capturing nuance, expert level refinement that skilled human make during improving AI generated content. And third, in addition to our expert editing, we also explored LLM-based editing to understand how automated approaches may compare to human experts. So we utilize two state-of-the-art models to edit the same machine-generated text as our human expert did. And here's a bit more detail on these two state-of-the-art models. You guys may have known Llama 3.5. They're later versions now, but it was a 70B instruct model and GPT-4 Omni, and these two models represent frontier in large language model, especially at the time of our research. Today we have models that have more thinking capabilities, and these models here doesn't have those capabilities. And I want to highlight that, a diverse model coverage ensures that our benchmark accurately captures real variety in machine-generated content that detectors encounter in practice. And this makes our findings more robust and generalizable across different types of LLM-generated tags. So to increase realism and diversity, we employed three distinct editing prompts for LLM edits, which have unique focus individually. The first prompt emphasized grammatical correctness and human-like qualities. The second aimed to remove typical AI artifacts, things like sure, here is the summary, and so on. And these are some of the instruction following from the reinforcement learning that these models exhibit. We try not to have that in our data. And third, we focus on producing more natural native sounding text. So this multi-prompt approach let us capture the diversity of how LLMs might be used for editing in real world scenario. And this is important because different user might give different instructions when asked an LLM to refine a piece of content. And the key question we're exploring is, can LLM edit their own outputs or outputs from other LLMs as effectively as human experts? And how do different editing instruction affect the final detectability of such content? And this gives us a comprehensive view of both human and automated editing approaches. So what did all of this work produce? Here is the scale and composition of Beemo. We created 19K examples with 9 different text version for each instance. And this include 2.2 K human written text, 2.2 K machine generated text, as well as 2.2K expert edited text and 13.1K LLM edited text across our different prompts and model. Our use case covered five practical categories that reflects how human actually use LLMs for like closed question answering, open question answering, open-ended generation, summarization, rewriting text. And these aren't just artificial tasks, they're real-world scenarios that we try to capture in the authorship domain. So now what we see in the pie chart, which I just speak about on the right, is the distribution across different text type. The larger blue section represents our LLM text showing a comprehensive coverage we achieve in multiple editing approaches. The scale and diversity makes Beemo one of the most comprehensive benchmark for studying multi-author text scenarios. We're not just testing one editing approach or one use case, we're capturing a full spectrum of how machine-generated content gets refined in practice. So how does Beemo compare to existing benchmark? And this table tells a compelling story. If you look at all of the red X's, most existing benchmark only tests the simple human versus machine scenario. Only a few recent work like Mixtex and LAMP at the bottom here, they made an attempt to add such edits or such mixed edits, but at a smaller scale compared to Beemo. So Beemo is unique. We're one of the first with both LLM edits and human edit text at scale, comprising of 19,000 K example across 10 models. And the bottom line here is that while other benchmark tests eccentric scenarios, Beemo tests the messy reality of how people actually use and edit AI content. So now let's talk about our experimental setup. We evaluated how current machine-generated detectors handle these complex authorship scenarios. We have four types of text: human written, machine generated, expert edited, LLM edit. And the key question here is, how do detectors classify these different versions? We designed seven binary classification scenarios to test different aspects of detection. For example, can detectors distinguish human written text from any type of machine generated content? And can they tell expert edit text from purely machine generated ones? So we tested 33 different detectors configuration, both in zero shot settings that don't require any training, and we use pre-trained models that are specifically trained on machine generated text, and they are trained to detect machine generated text. Our performance matrix is the Akarov area under the receiver curve, which tells us how well detectors can distinguish between two classes, like real and fake, or machine and some other category that we're interested in, across all possible decision threshold. And this comprehensive evaluation give us the first systematic look at how editing affects machine-generated text detection performance. So before we go into what we discover, I will take some questions here if you guys have any.
Yeah, great. Thank you. We have two questions. One, I'll just go with the first one. Many humans are not native speakers, so language errors can make text seem more human-like. And how do you approach this trade-off?
I mean, this is a critical question. The truth is, in recent years, we've seen that these large language models are, their distribution are getting closer and closer to human, but they're truly not quite there yet, right? But the latest models, they definitely are better at humanizing text than our prior GPT-2, GPT-3, or even GPT-4 models. They're really good. Um, yeah, so I think in this case, in real world scenarios, if I'm a user, I'm more concerned about how can I evade people understanding that my artifacts is less authentic and is more authentic than is artificial. So I would try to edit it in that from that perspective, and I will use the best available tools to do so. And of at that point, it would not be more. There is no cultural aspect in those cases. And these models are very biased culturally to language. Just English by itself, there's so much vernacular of English that they don't cover. In the United States, there are more than seven. And just think about the Caribbean islands and places in Germany where you speak a different vernacular of English. I don't think these models capture that in text nor in speech. But I do think we will get closer, maybe in the next 30 years, but with more data and more emphasis on, you know, speech and diversity and inclusion.
Okay. Thank
There was
you.
another question.
Second question by Kaiwei Lai. How worried are you that the dataset will be scraped and used to train future models?
Yeah, I think that is a definite concern. Now, if the data is used for good reasons, like developing more robust models, I'm very happy. Okay. Now, there are companies out there, if you're not aware, telling students, hey, you can use our platform to bypass your assignment, run it through and humanize your text. Now, for those reasons, I am very worried. But, as technology advanced from the beginning of fire to the computer and moving on to AI, people use technology for good and bad reasons. We have what is called unintended use, and we pray that people would utilize such technology for being productive, for helping, and to become better human beings as a support, not necessarily the opposite. But I think we have no control over the next half of the equation. Yeah.
Makes sense.
Okay. Thank
Yeah.
you. All right. So I will continue now to talk about what did we discover from our experiment. So here's our findings, and they're quite sticky. First, major results. Expert edited, so the expert-based editing successfully evade detection. So this is our first major finding. And if you look at the results table, you can see significant drops in the ROC scores when detectors try to identify expert edited text as machine generated. And some of these detectors see performance drop up to 22%. So what this means practically is that when skilled human edit AI generated content, current detection system often fail to recognize it's a machine generated text. And remember that scenario I posed at the beginning of the session about student editing with models like ChatGPT. This confirms that current detectors will struggle in exactly those scenarios. And this has major implication for anyone relying on automated detection system, whether in education, content moderation, academic integrity. the assumption that we can rely on these tools, I think would definitely have negative consequences, right? And this isn't a minor effect. I think it's a fundamental limitation in current detection approaches when faced with the reality of how people actually use these tools. And our second finding is that LLM texts are less likely to be recognized as human authored compared to expert edited ones. So this is fascinating because it reveals a key difference between human and machine edited capabilities. When we compare how detectors classify expert edited versus human edited text, the expert edited version are much more successful at appearing human-like. And this tells us that human editors bring something unique to the table that current LLMs can't fully replicate. So, skilled human editors understand the subtle nuances of natural language in ways that even our best, more frontier models don't quite capture yet. And that brings us back to one of the questions you asked. And and from a practical standpoint, this means that if someone wants to make AI generated content truly undetectable, have a human editor make significant edits to those um, than using an AI to polish it. So humans are pretty much better at making the AI content seems more realistic than even using another LLMs. I think in the past, people would have used several LLMs to humanize their text to evade detectors, but that doesn't work anymore. That don't really work much well anymore. So a third key finding is that zero-shot detector better distinguish human written and machine generated text compared to pre-trained detector. Yeah, and that is somewhat counterintuitive. Like, how does a trained model um, don't do well as a zero-shot detector? So this might, uh, we might expect the detector, especially trained on these tasks, to perform outperform methods that already not requiring training. But our results show that the zero shot approach, like if you look at the top there, binocular and log probability methods are more robust to editing scenarios that we tested. So why this happens, and we assume that the pre-trained detectors may overfit to the specific patterns they saw during training, and there's so many detectors out there and which I think make them more brittle when faced with editing content. There's so much LLMs out there. And the zero-shot methods, on the other hand, rely on fundamental properties of language models that is harder to fool through editing. So the practical takeaway is that simpler training-free approaches might actually be more reliable in real-world scenarios when we trying to develop tools to detect human and machine edited content. And this challenges the assumption that more sophisticated or trained models are always better than for machine generated detection. Sometimes the fundamental models are the best. And our fourth finding is most detectors show similar performance regardless of whether they edit or moderations are significant. So if you look at a graph here, it shows detector performance across different edit percentages, ranges from light edit 0 to 20% to heavy edit at the end, you see 80 to 100%. What's striking is that most detector maintain relatively stable performance across these ranges. And this tells us something important. It is not necessarily the amount of editing that matters, but rather the quality and type of editing being made. Even moderate expert editing can effectively evade detectors, while extensive editing doesn't necessarily make the text more or less detectable. Okay. And the practical implication is that someone doesn't need to completely rewrite AI-generated text to fool current detectors. Even modest, skilled editing can be quite effective. And as you notice that binocular consistently outperform or best model across all editing range, reinforcing our early findings about zero-shot detector robustness. And these results paint a clear picture. Current machine generated text detection systems are not ready for the reality of human AI collaborative writing. So let us summarize our key findings and the implication. First, machine-generated detectors often fail to recognize um, machine-generated text after experts have refined it. And this fundamental challenge, fundamental challenges really make it difficult for current detection system in our real-world case scenarios. Second, we can evade an AI detector by making just slight edits to machine-generated content. And this means the bar for fooling these systems is surprisingly low. You don't need to be an expert editor. You can generate your content, refine it with maybe some cleverness, and you will evade your mom, your teacher, or your professor. And third, expert edited texts are more likely to be classified as human written compared to LLM ones. And this reveals that human editing brings unique capabilities that current AI cannot fully replicate. So what's next uh, for the future? Um, yeah, so I would Yeah, before I talk about what next, I would say that LLM editing is not the same as human editing, and you can fully replicate human editing with LLMs. And this has important implication for everyone thinking about AI, for using it to completely detect um, edited text created by the people around us. And the bottom line in our research is that it shows that the current generation of machine-generated text is not equipped to handle the reality in our current collaborative writing, which is becoming a norm rather than, I would say, an exception. So, what needs to be done in the future? So we we want to open up several exciting research directions. First, we want to explore other machine-generated detection tasks beyond the binary classification. Things like authorship attribution, multi-way classification that can distinguish between human, machine, expert edited, LLM edited content, and even extracting a specific spans that were edited. So being able to tell you, hey, this is where it was edited and this is a person who did it. Being able to do that will create a lot of accountability, and I'm sure this task is very hard. Second, we're investigating supervised detectors' robustness when they are encountered on unseen instruction-tuned LLMs and new written tasks. So how well does these systems generalize beyond their training data is a really important question that based on the results that we saw. And third, we want to understand the effect of LLM edited content in training data. So if detection systems are trained on data sets that include LLM edited text, how does that affect their ability to generalize? So these directions will help us and help the community build more robust detection system that can handle the complex and multi-author scenarios that are becoming pretty much a standard practice. Ultimately, this research is about preparing for the future where human AI collaboration is the norm, not an exception. And I will thank you guys for your attention. And at this point, you can ask all of your remaining questions.
Thank you very much, Jason. Um, that what you mentioned about span detection, I have to say, sounds like sci-fi. Imagining if I imagine that the text will be annotated like sentence level by who's the author, that sounds completely crazy. And it's very exciting that your research is a step towards making that possible.
Yeah. Well, if you see it on the Jetson, it's going to happen soon. They seem to be good at predicting stuff. So, I hope in the I do hope in the future we are able to do this, but the community would know that this is pretty much a very difficult task because of the inherent nature of the large language models, the transformers, and what takes place inside of them. While we are more aware of how they work, we still have those hidden layers where things are not well explained. They are exhibiting new capabilities now, reasoning capabilities. We've seen that these models, with this ability to think, they have more accuracy in coming up with answers, solving very complex mathematical issues. Something that very similar to human, like we can have, if I ask you one and one, you might give me an immediate answer because you know one and one and two. It's almost like guessing. But when it comes to multiple steps, it's much difficult, and they're exhibiting these capabilities. Now, being able to track, these models in the future is a very important problem, but it's going to be a difficult task.
Very much so. So we have two questions. The first one is how good do you think a detector must be to be used, for example, in teaching, to reject AI-generated text? Because even small levels of errors can prevent the detector from being widely used.
Yeah, very good question. Yeah, I don't think they are very reliable at this time. So to totally, I think to say it's likely been used by this text is likely been there's likely collaboration with an AI model, yes, but to definitively say that the accuracy, the as you can see from the research, we cannot rely on the current models to do so for us. And also, we need a paradigm shift. I think AI is integrating in all aspects of our system. So now we need to think about, how do we use them positively? How can we change our classroom setting in the way we deliver work so it's not easily reproducible? And how can we encourage students to use these technology to help them enhance their learning, right? Because they have a lot of benefits for people with dyslexia and so on. I have dyslexia. And I know the benefit of using this technology, whether it's for text to speech and for helping with writing and so on. I think the narrative has to change. They are friends, not foes. And coming up with a creative way would take a lot of work and effort and investment and how we can best integrate with them, not necessarily use them, but it's critical. It is very critical to be able to know for academic integrity and so on that your students are not just using AI models to do their work. Yes.
Very good. Next question is proving content is AI generated in court is an absolutely fascinating topic, text specifically. From a linguistic standpoint, text has way less variation than images, so there will be never be a way to prove a text is LLM generated without a reasonable doubt. This is very important for the cases when generate written text is flagged as AI generated. Okay, not directly a question, but court is definitely
Yeah. Can
um,
can
a
you repeat
case.
it one more time? Can you repeat it one more time?
So it wasn't exactly a question. Basically, it was
Yeah.
telling that the that the usage in court is absolutely fascinating,
Yes,
and text has less variation than images.
yes.
And maybe it will be impossible to prove that something is LLM generated without, like, beyond reasonable doubt.
Yeah, I think it's going to be tricky. And with the current vulnerabilities in our models, um, it's going to be hard to do so. And not just that, is the ability of other people to trick. Let's say I have a court case and I'm trying to prove that this work isn't is my work is not human generated. Some people know how to bypass the alignment of the model to tell it, hey, yeah, this is Jason's work, um this is not AI work. I can just do a prompt attack, and I can put an image, a matter of fact, and put something called projected Gaussian descent, which is noise on the image that you can't really see, and get the model to give me the outcome that I want. So there's a lot of risk in when it comes to high stakes scenarios where we're going to use them for medicine, for court cases, for advancing science, for doing highly classified work. But the world is at a race to who is going to be on top, who is going to be leading this AI revolution. So there's research that would consistently advance regardless. Okay. However, I think that's a very important point that you make. It's going to be hard in those high stakes scenarios, like in the courtroom. There will be cases where we use them for condensing text, for condensing laws, and just making things easily digestible, which I think is needed in many institutions like the justice system. They will have a lot of use cases. But when using them for critical decision making processes, I think we need to slowly move in that direction. Yeah, so great thought. Although it wasn't a question, I think it was very relevant. Yeah.
Yes. Okay. Very good. Any more questions from anybody in the audience? If not, we usually just ask our speakers what you are particularly excited about. Any research, not it doesn't have to be your own, something that you are particularly excited right now about.
Yeah. Yeah, I'm actually delving into reasoning at the moment. Very excited about that. And the research that I'm doing at my current internship is very cutting edge. Um, so I think I wake up every morning very happy about the research, although it can be very difficult. And I'm trying to hone in on the reasoning capabilities of these models and, look at how we can measure those, and I think it's an open question now that some researchers I think are excited about as well. Because if we can answer this question, we can understand the pathways in which these models think and how they make decisions, and that they have multiple pathways in doing so. And it can come from just changing some parameters, like temperature, you know, um, and yeah, so it's really critical because I want to understand how we can hone in on these strengths and weaknesses in these models and use them collaboratively to address some of the most pressing concern. So this is some of the work I'm very excited about. And of course, my research is in the multilingual space. So anything multilingual, um, my mentor, Adaku, who's on the call, she sends me a lot of multilingual papers almost every morning. Some of them give me heart attacks because so sometimes they are just aligning with all the ideas I have. It's not a great feeling, but it's an exciting space to be in as well. Yeah, so these are my excitements every day. Yeah.
Thank you. Yeah, reasoning is super exciting. A lot of papers coming out, and I think we'll see a lot more advances in this space, and hopefully you can also contribute to that.
Oh, absolutely. I'm definitely looking forward to contributing in that multilingual space. Maybe I will have some works coming out soon, and yeah, I'm definitely excited. And perhaps I'll give a next talk when I make some leaps a few steps ahead.
Awesome, Jason. We're happy to have you next time when on your next paper. So, yeah, having said that, thank you very much for your time. Have a nice day, everybody. A big applause to Jason Lucas, and yeah, we'll be uploading the video, and you can use the link. Just pass it on to use it for your whatever you like to use it, and yeah.
Yeah, thank you everyone who attended. Thanks to all the collaborators who joined, and thank you guys for having me. This has been a great talk, and it was a great pleasure doing this. Thank you guys so much.
Mhm.
Thank you, Jason.
Nice.
But thank you.
You're
Thank
so welcome. I enjoyed it thoroughly. Okay.
Yeah, thank
Bye.
you. Yeah,
You're
for
most
the
welcome. Thank you. Bye,
yes.
Doc.
Yes, thank you.